In our last session, we answered the big question, which method should I use? You learned how to choose the overall strategy for your mesh from sweep to tetrahedrons. You became the architect of the mesh. Today, we go one level deeper. We will learn how to take precise local control of our mesh to add detail exactly where it is needed. We are moving from global sizing to local sizing. So, by the end of this session, what will you learn? First, you will learn how to apply specific size controls to bodies, faces, edges, and even single vertices. Second, you will master the critical behavior setting, telling ANSYS if your rules are a suggestion or a command. And finally, you will learn how to use bias to create a smooth, high-quality transition between the small and large cells. Welcome back, everybody, to session 6 of our ANSYS machine course. The thing is, in our previous session, we learned how to deal with the multi-zone and the rest of the mesh methods. And if you remember this microchannel with micro pin fins, we could successfully increase the quality of this by using and applying different methods. For example, as you see, regarding 4 millimeters element size, the quality of this current microchannel is about 0.21 in terms of orthogonal quality. And simply by just applying a mesh method, which is multigrid, which acts like actually wise and intelligent sweep method, we could drastically change the minimum orthogonal quality. And you can see it right now. If I get back to mesh, I can recheck my orthogonal quality, and right now the minimum shows 0.65. In the current session, we are going deeper, and in this session, we are going to focus on the sizing, of course, local sizing, because we covered global sizing in session 3, and this time we should see how to apply a specific size only on a local entity, such as an edge, such as a surface, or the whole body. In order to apply this, right-click on Mesh, following Insert, you would see the sizing. So this sizing could be applied on different entities. If you check the upper toolbar, you have access to vertex selection, edge selection, face selection, and finally body selection. And you can simply apply it on the whole body, the faces, or the edges and vertices. So the features and the parameters is somehow different for either of them. So let's start from the biggest one, which is volume or body selection. Of course, because we have only one body in here, it doesn't mean so much, because if you have a complex geometry made out of several bodies, it would be much better to use the body sizing. Otherwise, for the current one, you can just simply get back to mesh and use the global sizing, and it will affect the whole body. So it's somehow meaningless to use body sizing for just one component. As you can see in here, we have different types of sizing definition. Starting with element size, a sphere of the influence, and then body of influence and factor of global size. The point is that the body of influence is very, very important, and we need a separate session. I guess it would be session 7, and we will cover it individually. But the rest of them will be covered by the end of this session, and they're actually important as well. And also, in the advanced sizing, we have some other options regarding the curvature and proximity, which we call them advanced size function, and they will be covered in a separate session as well. We actually have them in the global sizing, but at this time, due to their importance and because of their crucial effect on many different geometries, we need them, and we will get back to them later. So for now, let's see what do we have for types of definition. The first option, which is the most common one, is the element size. This is the most direct tool. You select a face, edge, or a body and tell ANSYS the exact element size you want there. So for this body, as you see, the general sizing was 4 millimeters, but we can just decrease that to something lower than that. And by the way, this is an important point that solver prioritize your local sizing rather than the general sizing. And right now, if I get back to here, you would see that the size of elements has just decreased, and also the orthogonal quality increased to 0.83, which shows that by only applying body sizing on a specific entity, we can dramatically change the quality of our grid. But we have another option, which is the sphere of influence. The point is that it is somehow like a virtual sphere. And instead of a size, you specify exactly how many elements you want along that specific line. This is a very clever tool. It lets you refine everything inside a virtual sphere without selecting lots of geometry. So if I actually get back to the previous mesh that we created using 4 millimeters, you can see that we have some, uh, let's say, poor grids exactly around the things, and we can just investigate it by selecting this, and you can see the pore elements are generated around this fin. So using the body sizing, or better to say the sphere of influence, gives us the option to just draw a virtual sphere around any point that we want to actually decrease the size of elements around it without actually creating the wall. So the software asks for the sphere center, and as you can see in the list, we can just use global coordinate system, or any other coordinate system that we previously created. Uh, in the tree alpha, you will see the coordinate system. And if you, for example, want to define a coordinate system on this vertex, you just need to select this first, such as what I'm doing right now. And then by right clicking and inserting a new coordinate system, you can simply apply it. Or if you want to change the geometry, you can just define another point for it. So if I get back to our sphere of influence and the sphere center, we can see coordinate system right now. So for this sphere radius, regarding our current model dimensions, we can, for example, come up with 2 millimeters, and the element size around this point would be 2 millimeters. So if I update the mesh once again, actually I need to unsuppress this. And right now, if you get back to sphere radius, you can see a preview of that regarding 2 millimeter sphere that we just created. So let's update the mesh to see what is going on and how it affects. And once again, if I get back to here, you can see that we cannot see a sudden decrease in element size because we applied 4 millimeters here. So maybe I'd be better to actually decrease the element size in here, and we can affect a actually bigger region right now. Very well. So as you can see right now, around this point regarding the virtual sphere that we created, we could successfully actually decrease the size of the elements, but just around it and nothing anywhere else. So this is how the sphere of influence can help us, but don't forget that it is not recommended in most of the applications because we better have a body of influence that you'll learn in the next session instead of this. But in some cases, when you have some poor grids around this specific region, it can be helpful. So the next option for body sizing is the body of influence that we will cover in next session. And finally, the factor of global size. Actually, the title suggests that we're going to define a factor of the global size that we detected and defined previously in the default settings. So right here, if you put factor of 1, you can see that the element size is equal to global sizing. And if I put down, for example, half of it, you would see just half of the global sizing. So this may not be somehow a useful tool. And among all of them, for now, element size is a priority choice. But what if we select a face instead of a body. For example, in the current model, we know that the poor elements are around the fins. So maybe by just defining a smaller grids around the fins, we can increase the quality of our actually body part. So in this situation, we better, for example, detect the faces that are actually sensible, and it could be the pin fix. So holding down the control key, I would be able to select these faces all together. And what I'm going to do is applying local sizing on all of these fits. And one more time, maybe we can have 1 millimeter on all of these faces. And for the other parts of the body, the ANSYS will follow the global size that we defined previously. And this is the result. We can see that it exactly followed our lead, and it could create smaller greens around the fits. So this was how we could apply face sizing. And once again, for this, you can see the same definition types. But the story has changed if we define edge instead of body or face. For example, let's say we want to have a smaller grid when actually we have the interest region on the left side of our macro channel. So this time I want to apply local sizing on these two edges. And around these edges, because of this corner and the flow behavior near that, we may see and expect some complexity and actually turbulence effect. So this time I want to apply the element size on these edges, but as you see the list, this time we have some other options, which is called number of divisions. Of course, it title actually presents that by using this, we must enter the number of divisions for these edges. For example, 100. So let's generate to see what's going on right now. And this is the result. As you can see, the software could exactly apply and actually divide these edges into 100 divisions. And this is how we can generate a structured grid, especially which can be very helpful because we need to have equal number of divisions for different edges when it comes to structured grids. And this option helps us. So, before proceeding, I want to mention one more thing, and it is about the behavior that you can see in here, which gives us two options, soft or hard. Now, after I apply a local size, we have a critical choice to make, its behavior. The default is soft. Think of this as a suggestion. The measure will try to meet your size, but it will prioritize a smooth, gradual transition to its neighbors. It's the safer option. And the other option is hard. This is a strict command. The measure must obey the size you set. This gives you absolute control, but be careful. It can create sharp transitions. So for our current model, maybe the soft shows us the smooth transition from these edge sizing to the global sizing that we can see in here. But if we just change it to hard, of course, it may just not affect it right now because up to now we actually had a hard and equal 100 divisions over these edges. But right now, if I change it to hard, you can see that it exactly try to follow our lead, or better say our command, because it's a must-do thing, not a suggestion anymore. So this once again could be a very beneficial in a structured grid generation process, and we use it later on in our practical examples. So for now, I'll just get back to soft, and as our very final choice, I pick up the Vertex selection tool. So as the title suggests, once again, we can apply local sizing on the vertex. It is exactly uh, follows the sphere of influence process. It asks for a sphere radius and also element size. Regarding the values that we specified, we expect a smaller grids around this region of the vertices and actually the global size for the rest of the parts. And you can see exactly it happened. So up to now, we covered the body, the face, the edge and vertices, local sizing, and also the behavior that we detected. And let me just get back to the edge. There is one more thing has left in here, and it is about the edge. If you get back to element size or number of divisions, you would see another section called the bias down here. You can see that only if you apply an edge. So finally, let's talk about the distribution of elements. Sometimes just setting the number of elements on the edge isn't enough. We need to control where they are placed. This is where we use bias. As you can see, bias lets us cluster nodes at one end, both ends, or the center. This is critical for things like bound layers and some parts that we may need to have denser grid, like our microchannel that we need denser grid near the entrance and the outlet, not in the center of the microchannel. So this is critical, and we need to apply it on many models. And the main control is the bias factor. It's the simple ratio of the largest element to the smallest element on that edge. A higher factor means a more aggressive clustering of the mesh. So let's apply it on our current model. I want to just have denser grid around my entrance region, which is on the left side. And after defining 100 number of divisions, I want to apply a bias type. As you saw, we have different types of definition, but as we already know, we need to have a smaller grid just on one side. So I simply select that. And this is where the software asks for the bias option. We've got two options: a smooth transition, which has us for a bias growth rate, which shows us a gradual increase in size, as you can see in the preview. And of course, by using a higher smooth growth rate, we can have actually a harsh transition. But in most cases, we use bias factor. And in here, what software asks is the actually the ratio of the largest element size to the smallest one. So, for example, if I put 5, I expect to have an element on one side 5 times bigger than the other side. So because we considered this area as the entrance region, we already know that the denser grid must be completely inversed. And let's check the other side. It is exactly wrong for the other side as well. So in these scenarios, we have another option, which is reverse bias. All we need to do is to select the edges that we can see a wrong transition and distribution in the preview. So both are incorrect, and we need to apply it completely different right now. And as you can see in the preview, it has just modified, and we can generate the grid using bias factor right now. And this is the final result. As you can see, we have actually a smallest element right in the entry of the microchannel. It is 5 times actually smaller than the other side. That's what we can see in here. So we covered the body sizing, the face sizing, and the edge and vertices sizing on this microchannel, but we left the advanced size function and also body of influence for the next sessions that I suggest you to follow, because these sessions are the core of ANSYS meshing, and you, in most cases and scenarios, you need to know these sessions, and the advanced option might be helpful somehow in just critical or complex geometries, not in all of them.